this Hydro Builder portrait is available only for a smaller group of DRIHM portal users. So if you have such a portrait, probably we made a mistake in approving your application to the portal. The idea here is that only expert in model configuration should be allowed to include a new model to the portal. So this is restricted to a limited set of users. Up to now we are supporting those 3 models. The idea here is to let model developer to upload all the configuration data, set all the configuration parameters that are useful for the calibration of a new model. Up to now, all those data are kept on the portal. We are considering the option to automatically upload also those data to the catalog. So produce the metadata relevant for the catalog and give the user the possibility to search for the model instances directly from there. Is not yet available, so up to now our model has been required to do essentially such an activity twice. Let's go ahead for a second with RIPS. The idea is that we have to specify the geographical constraints, and then we can select a few model-specific parameters that probably is better to discuss with Luis. So,
okay, so I've just prepared a few slides to show you how you can contribute a new model instance and even a new model to the DRIHM infrastructure. Let's discuss the model instance first. In order to be able to contribute a new model instance, you have to make all your local data available to model users within the DRIHM infrastructure. So the idea is that the model run will be executed in an unknown machine, in an unknown place, but under certain control conditions. The idea is that we will have a directory where our model configuration files will be stored and where the job will be executed. What we have to do is to take our local configuration files and wrap them into a package that can be submitted to the DRIHM portal, and then it will go there. From the DRIHM portal, it will go to any place, to whatever the machine the model is going to be executed. So these are the data that we have locally installed in our machine. We are using our model, RIPS, and we have decided to organize the data, for instance, following this strategy. There are several case studies that we are analyzing, several basins. So we allocate one directory per basin, and then in each basin, we need to have a directory for static data, which are the geomorphologic configuration data that are derived from the digital elevation model and from the soil types. We also have the initial state data, which are the initial water table configuration files. And finally, we have some shell scripts that we use to run the model and all the associated utilities. Now, when we run the model, we apply to a number of individual storm events. So for each storm event, we create a new directory, and for each directory, we store the rainfall input files, the state variables for the model, if we want to check that, and the final hydrographs. So this is our local configuration for RIPS. The way RIPS is executed locally is you go into the command line, you prepare it to run, and then from the command line, you let it run. There is also a user interface associated to it, but I would not like to discuss that one. We can run it from the command line. So our task, our job now is to separate RIPS from our local installation so that it can be run in any machine. In order to do that, what we have to do is to isolate all the data files that are required to do a single model run, not a whole lot of model runs that we are using locally, maybe to calibrate the model or to understand to run under different conditions for different episodes. Group together all the data that are required for one single run. This is relatively easy to do because you have to select the shell scripts, the set of initial water tables that might be required for from one run, the geomorphologic configuration files, and then the files that you get for one single run, for just one episode. Now, what we do with that is we package it so that it can be run within DRIHM. Within DRIHM, what we do, as we saw yesterday or day before yesterday, is that we get a netcdf file. From that netcdf, we apply the pre-bridge, and we generate the rainfall input files. Then we run the model, and finally, from the output generated by the model, we apply the Q-bridge and transform those output files in our common data standard WaterML files. So basically, the sequence of operations is first, run the P-bridge, second, run the model, and third, run the Q-bridge. We have to organize this sequence of operations in a way that they can be run in any machine. That means that in our shell scripts, we will have to use relative directory reference, not absolute paths, but relative paths, because we will not know where the model is going to be run. We have to make the effort of remove all global references in our path directory. RIPS has a special feature, which is not very common, but is required for DRIHM. And that feature is that these files, these configuration files and the rainfall input files are binaries. RIPS was developed many years ago, and it used a unique binary standard for data. This means that if data are in binary and they are moved from one machine to another, since we don't know the platform where the machine is going to run, where the model is going to run, the binaries may not work, depending on the processor and depending on whether it's a 32-bit or 64-bit operating system, it may not be able to run. So in order to allow the model to be run in any machine, what we decided to do was to put the original files not in binary format, but in ASCII format. And that's why there is a shell script here that is called from ASCII to bin. It means that you have your original data in ASCII format, text files, and then they are moved into binary formats that RIPS can understand and executed locally. That's why we need this previous transformation from text files to binary files. But this may not be the case for all models. What will be the case for all models is the fact that you have to run first the P-bridge, then run the model, and finally run the Q-bridge. Okay, so what we do is to build what we call a RIPS model instance. The model instance is just a version of the RIPS model that is going to be executed for a given basin and for a given episode, for a given event. This is just a replication of the data files that we have as input to our RIPS model, but the permanent data, the episode, the event data will be provided by the P-bridge. Therefore, we only need the static geomorphologic data. As you can see here, they are referred to in ASCII format, not binaries, but ASCII. The initial water table configuration files that are also defined in ASCII format, in text format, and all the shell scripts that we are using to run the model. This from ASCII to bin is the one that you use to transform from text files to binary files. The RainNet CDF SH is the rainfall bridge, the P bridge that you use to extract the rainfall information from the NetCDF file and put it into the binary format that RIPS can understand. Then is the simulation basin, a simulation script, which is the actual model run, specifying everything in terms of paths relative to the job directory that we are going to use. And finally, the results, the result, which is the result, the Q bridge, where you take the RIPS results in binary format and transform them into a WaterML format that can be understood by DRIHM. This is just the sample WaterML file that is taken as input for the Q bridge in order to take all the relevant information for that particular model run or for that particular basin and include it into the WaterML file. So everything is nicely packaged in three directories. Then we have the DRIHM out directory to store the output files. And in addition to that, we need to add 2 new shell scripts that are being used by the system to run this model, to run the model. These 2 files are the execution SH, which is a generic file, a generic shell script that all models have to prepare. And it's the file that will be the shell script that will be executed by DRIHM when they want the model to be executed. A script for all models that are included in DRIHM. So the version of execution that we are using in our model instance, what we do is to call a specific model, a specific shell script that contains all the information relative to that specific model instance. All right, so from that, what we do is, as we saw yesterday, is follow the data flow. The rips.sh is the command script that is being used by DRIHM to run drips. And this rips.h will be performing a sequence of operations. The first one is to extract the input file. The input file is a compressed tar file where you put all the data and command scripts that are required to run the model. So rips.sh, it first will explode, will decompress this file and create all the working environment for rips. Then the execution.sh will take as argument the input, the file that is prepared by the DRIHM portal when you configure the model run, that we call namelist.input. And then we organize the execution in order to be able to use the information provided by the set of parameters included in namelist.input and feed it to the local shell scripts that performs each of the 3 sequential tasks that I just described. The DRIHM Bisanyo will execute the model starting with the P bridge, then it will run the model, and finally it will run the Q bridge. And each of these shell scripts will take the appropriate, the adequate input parameters that are passed by the portal. Okay, so afterwards, the rips shell script will take the output file and we will generate a compressed tar file that is passed to the portal to distribution for the user. So our job here is to organize this data flow, these shell scripts, so that they can be run in any unknown machine. You can test it locally in your own environment, and once you are ready, you upload all that information and see if it runs in the DRIHM environment. I can tell you that it may look like a complex task, but once you realize what is required from you, it's really not that difficult. Since we were developing the system, it took us some time until we understood what was required from us. But I can tell you that once you understand it, it's really a relatively simple task if your model is well designed to be run from the command script, from the command line. There are other models that are really tightly coupled with a user interface, and for these type of models, it is relatively more difficult to separate the actual model run from the user interface and prepare all these shell scripts to be able to run that. Okay, now once you have done the design, once you have separated whatever is required to do just one model run and put it into an input TGC file, introducing the data in the portal is very straightforward because the portal has been designed to receive the data that we actually required. As Emanuele just told us, first we select the model that we want to include for the data, and then we are shown with a geographic screen where we introduce the coordinates of the bounding rectangle, which is this rectangle over here. And then optionally, you can include a shape file and a digital elevation map file, digital elevation model file, to describe the basin boundaries so that the user can identify the basin where the model is going to be run much with more accuracy than with just the boundary rectangle, and the digital elevation model to obtain information on how the basin drainage is configured, etc. This is the first step. The second step in the general configuration is to describe the points where your model will produce hydrographs. Some hydrologic models only produce hydrographs at the basin outlet, and for those models we only select one point. But semi-distributed models and distributed models usually can produce hydrographs at any location within the basin. So we can select as many points as we want to identify as hydrograph locations. We introduce them by defining the coordinates of the point and giving to each of these points a name. As you introduce these coordinates, you will see this sign, Google sign, that appears in the map. So it is a good opportunity to verify that your coordinates are actually on the river. Sometimes, if you fail with your coordinate identification, you realize that the coordinates you are giving are not on the river. And this is a good opportunity to verify that your information is correct. Okay, these two slides that I just showed are common to all hydrologic models. All models will have to include the bounding rectangle, they will have to include the basin boundaries, the digital elevation model, and the hydrograph points. Then there is another section in the model builder to include model-specific data. And in that case, it has been specially configured for grips. We have decided what information will be defined by the model builder and what information for the model run will be provided by the model user. And this is a design decision. You, as a designer, may decide to define some model parameters yourself, whereas other model parameters you can allow the user to select. Okay? For instance, I made the decision to specify the computation time step of the model beforehand. Why? Well, because I was not sure that any model user would be able to select the appropriate computation time step. But that could have been left to be decided by the user, whether you want to run the model every 5 minutes, or every hour, or every 15 minutes. Okay? So it's a design decision. It's not something that has to be adopted permanently. In other cases, it is very clear that some data have to be provided because they are specific for a given model run. For instance, the initial condition of the basin. We cannot think of having a hydrologic model that always runs with the same initial condition, be it wet, average, or dry. So we had to let the user decide and choose whether he or she wanted to have a dry, wet, or intermediate initial condition. That's why we provided a number of gradually varying initial condition files, and we decided that we were going to let the user choose a number between 1 and the maximum number of initial condition files in order to specify the model initial condition. In this case, we chose to have 10 initial condition files in our configuration, and therefore the number included here is a 10. The second data that we decided to let the user choose was the calibration data set that we are going to use. In the case of drift, we are allowing the user to define the actual value for model parameters. But in the case of RIPS, since model parameters do not have a clear physical meaning, at least not all of them, we prefer to calibrate the models beforehand for that basin, and once the model is calibrated, share the optimal parameter values that we obtain in the calibration with the model user. There are 4 parameter values that need to be used, and they are called parameter A, B, C, and D that correspond to RIPS basic calibration parameters: the degrees of hydraulic conductivity with depth, the anisotropy ratio, the ratio between stream and hill slope velocity, and one of the velocities that I think, to run it in a probabilistic way, only amounts to running the model several times, each with a set of parameters sampled from a random distribution. So in calibration, we characterize the probability distribution of model parameters, and then we sample from those probability distributions and generate the model, generate a number of model runs with these parameter values sampled from the probability distribution. In order to specify a probabilistic calibration, what you do is you sample parameter values from their probability distributions and introduce into the portal the different sets of parameter values. And you can do this for a set of calibration strategies that you want to include. If you only have one, you just introduce one. But if you've worked with several calibration strategies and you want to let the user choose which of those is more adequate for his or her own case study, then you can allow them to choose that. So at the end, after introducing the initial condition files, and for instance here we have 2 calibration strategies that we call initial and random, you can visualize the results. And if you select one of those strategies, you can even see the deterministic calibration and the values for the probabilistic calibration. So the portal is prepared so that you can introduce the information in an easy way. After you've included all the data, you are offered a text space, a text box, to introduce a brief description of this model instance, where you specify, okay, this is a model instance that has been prepared for the RIPS model and the Bisagno basin with this original digital elevation model and with this resolution, etc., whatever you want to include there, and click on submit. And once you click on submit, after a while, you get the message that uploading was complete. So there are 2 parts of preparing the data for the portal. The first part is getting organized yourself and preparing all your configuration files, structuring them in a way that they can be packaged in a bundle, in an input TGC file that can move around and be executed on any machine. And the second part is prepare all the information that is required by other model users in order to interact with your model instance. For instance, in order to interact with meteorological models, we need to specify the bounding rectangle or the basin boundaries. And in order to interact with hydraulic models, we need to specify the outlet points, the hydrograph points that we are being generated. Once you specify that information, the rest of the technicalities regarding model execution is hidden from the user, and the user sees the model only as a black box that can interact with meteor models and with hydraulic models in a smooth way. I think this is it. Okay.
Thanks. Okay, just to give you a quick overview on the drift part, the first tab is essentially reporting the same.
Essentially, for drift is more or less the same that Luis presented for RIBS. You have to create a data structure to have a right model instance on the portal. We have to create a structure in this way, so I have a main directory with in the root we have the model scripts and the model executables and the model settings file, and in a data directory you have to put the data static and the data info and all and for the dynamic data we have another directory with inside we have to put the forecast data, the observer data, and at the end the portal will store the results data in the outcome folder. Essentially, you have to create this situation, and we have to upload in the portal for the static data the files, the static files for the drift model in this way. And the structure and in the grid run, we have a bash script that search an input compressed file, and this compressed file have this structure that is the same that we have to upload in the portal, in the Hydro builder, for having a good right run of the drift model. And in the portal, the situation is the same that we have seen for seen for RIBS model. We have to put the boundary of the domain, upload the DEM file. Just a technical note, because usually you have the ASCII grid, but you don't have the KML file. A good idea is to use, for example, the GDAL libraries to convert your ASCII file into a KML file. Then you have to put, you have to upload, if you want, the DEM file and the KML file, and add your outlet point section where you want to have the initial results for your run. In the model specific, you have to put the value for the three parameters of the drift model. For example, for the first line is for the field capacity parameter, the second line is for the infiltration rate saturation, and the third line is for the soil humidity initial condition. Also, because drift needs to run also an observer data, you have to select the box for the observer data. And finally, you have to submit the data that you have uploaded for your drift run, and if you want to put some useful information, for example, my best run in my life for drift model. So, yes, okay. Nothing.
Thanks, Luis Andri and Fabio, sorry. This is all for the introduction of new model instances. Again, this is a portrait that support model builders including new instances, so they can essentially decide which is the degrees of freedom let to the user, even letting a different range of meters, so we can essentially grant that the user is going to produce simulations that are meaningful. So thanks again to Luis and Fabio, and probably now we have a break.